So we started with angular momentum of a particle as the moment of linear momentum. We got the equations of motion in terms of angular motion and impulse and momentum. So we realized that the summation of moments is the change of angular momentum for the particle. We extend that to rigid body, got this equation to calculate the angular momentum of a rigid body using, tiny momentums of each particle. We simplify that for angular momentum about g, angular momentum about fixed point. Then for the three types of motion, translation, rotation, and general motion, this is how linear and angular momentum work, right? So for translation, there's no angular momentum because omega is 0. For rotation, you can simplify it as just the angular momentum about the fixed point. And for general motion, you have linear momentum that comes from velocity of the center of mass and angular momentum, which comes from omega and moment of inertia about the center of mass. We got these equations for linear angular momentum. Then we did the principle of impulse and momentum, initial linear momentum of the system. And remember, when you calculate the linear momentum of a rigid body, we use the velocity of g. The initial linear momentum plus external impulse gives you final momentum. The initial angular momentum plus external angular impulse gives you final angular momentum. This is what we did the other day. And we said, okay, if there's no force or moment applied, initial and final linear and angular momentum will be the same. This is the conservation of momentum for rigid bodies. You saw that in cases like ice skating, or even the video I showed you here, when there's no external force or moment, if you change the direction of rotation, or if you change the moment of inertia, the angular velocity has to change to make the overall angular momentum the same. This is when you see you create an angular momentum in z, the guy rotates otherwise. To cancel that, he reverses the angular momentum about z, and his own rotation is reversed. This is what we did. We did some examples. Now, you remember in chapter 15, after linear momentum and impulse, we used those equations to analyze impact. We're going to do the same here. The only difference is when you have rigid body, you don't have only linear momentum. You also have angular momentum, and it makes the case slightly different. So let's say you have two rigid bodies, like one of them is pinned here, right? And the other one is just a particle moving around. At the impact point, again, you have two surfaces coming into contact. The surfaces could be flat, could have like different curvatures. As you see here, I can zoom a little bit here, and you may see that you have one curvature here for the green object. You have another curvature for the blue object. The plane of impact is tangent to two curves, and the line of impact goes through perpendicular to this, goes through the in contact point, right? We had the same thing for particles. So this part doesn't make a big difference. Overall geometry is the same. For the rigid body, we're dealing with center of mass again. Now, let me ask you this question. Assume that this blue object is at rest. It doesn't have to be as at rest, but I try to kind of simplify it, right? If this green object comes and hits this here, where we have large impulsive forces. We're going to create large impulsive forces, but the question is where? Come on, guys. Should I ask someone like Chris? Chris, do you hear us? Heisey. In this impact, this blue object is addressed. The green comes and hits it. Where the impulsive, remember what we called impulsive force? Forces that are very large and applied at a very small period of time, like fraction of second, maybe millisecond, few milliseconds like that, right? So where we get these forces here?
I think it's at point C.
At the contact point. And that, do you think that is the only point that you have large forces?
No, but I'm not sure.
Okay, let's see how, Andrew. Heisey says we have large impulsive forces at contact, which is true. And we kind of knew it from chapter 15. Do we have any other large forces created? And when I say large force, the gravity is not part of it. You remember we said gravity, the basic forces that you deal with, or let's call it ordinary forces, they're not large enough to have a large impact in very small period of time. So the impulsive forces are, as I said, very large. Do we have other impulsive forces, or this is the only one?
I don't think there are any more.
You don't think there's any more? Kelly, how about you?
Would there be some like kind of at A, because the green like G1 would like bounce back?
If it bounces back, it's because of the force. We are not talking about the motion. We are talking about the forces, right? Let's say, I don't know if you can see, let's say this is one object and this is another object, rigid bodies, right? It's like hanging here. This hits the other object with some speed. So the forces are large here. Heisey was right that there's going to be impulsive forces here. The question is there any other impulsive force? Andrew says no. What do you think, Kelly?
I would say no.
You would say no. I think most of you think no, but probably with the way I asked this question and emphasize, there's possibly large forces somewhere else, right? And I tell you where. What happens at this pin? If A applies a force to B, you're going to have some forces created at C. There's going to be definitely reaction forces at pin, right? Do you think those reaction forces are large and impulsive, or they're small and negligible? Say something. Haojin, do you think the reaction forces at O are like small regular forces like gravity and other stuff, or they're also big? Haojin, do you hear us?
Oh, yeah.
What is your thinking? It's okay if you're right or wrong. I just wanted you guys to think about it and analyze it. I told you before, it's important to be able to analyze a system that is given to you fresh, right? let me switch to the tablet. I'm going to draw the same thing. I'm just going to add the reaction forces at point O, nothing specific. But I'm going to give an example to understand if those forces are large or not. Something that is maybe more tangible, and maybe many of you have already experienced it. So let's say this is the blue object, right? Pinned here, point O. We call this as object B. It has a center of gravity somewhere here, doesn't matter where, but somewhere here, right? And then the green object is going to hit it at this point. Let me just make it nicer, right? This is object A. Its center of mass is somewhere like here. Now, as you saw, we're going to have the plane of impact and line of impact like this, right? And we call this point C. This is the contact point C. Definitely, at contact point C, there will be large impulsive forces. You remember why I look for impulsive forces? Because we can neglect other forces, right? Because they said there are small impulsive forces. Now, I'm going to give you an example. You guys, I suppose maybe all of you or most of you have used hammer, right? Hammer is not something crazy, right? You just use hammer to hit something. Technically, when you use a hammer to hit a nail or, I don't know, something else to fix something or flatten something, the hammer, and let's just draw the hammer here. Let's say this is a hammer, right? You have something like this. And it comes with the handle. Oops. Right? And you want to hit a nail, maybe very thick, big, strong nail is not going to go in the wood easily. So you have like this nail here. What happens when you hit this? There's going to be impulsive forces, large impulsive forces between the hammer and the nail. Like these are like F impulsive force, which means it is large and it happens in a small time, maybe like in millisecond. Now, when you hold this hammer with your hand, right? Let's say you hold this hammer with your hand. This is not as bad as Mickey Mouse hand. When you do this, what happens? If you hit the hammer a few times, do you feel pain in your hand? Have you ever done that? You guys never use hammer? Come on. You guys were spoiled as a kid, I guess, right? So if you hit a hammer, if you have not done it, I'm sure you all have a hammer at home. Take it, find a piece of metal, and hit the hammer with the metal. After like maybe 5, 10, if you look at your hand, it gets red and it's painful. Why? Because when you hit this with this large force, when you hit the nail with this large force, the reaction forces that is applied to your hand from the hammer handle is also very large. Sometimes even if you don't hold it strong, you hit the hammer, it bounces and kind of escapes your hand, right? Because you have to hold it very strong. What that means is this: if F is impulsive, which means it is large and happens in a small time, then the reaction forces created in the hand are also large and impulsive, right? Which means you cannot ignore those forces, okay? You have to consider them when you analyze the impact. Does that make sense? Can you physically feel it? Anything you have with the large forces like rigid body things, if you hold it with your hand, I'm sure you're going to experience that large forces. It's actually painful. The force is too large. If you hit it very strong with like a, I mean, these are small hammers. If you get the big ones with the heavy head, when you hit it, it's actually painful. Why? Because the forces created here, like reaction forces, X and Y or whatever you have, those forces are very large and kind of hurts your hand. Now let's go back here. The forces we get in this impact of two rigid bodies, right? You're going to have a force like F A to B, and then you have the reaction force FB to A. And you know FA to B is equal to FB to A, obviously, but you can also have reaction forces here, and these are impulsive, which means unlike gravity, let's I put gravity here. You have mg and you have mg, right? You can ignore mg because it is much smaller than impact force and reaction force. But you cannot ignore reaction force Rx and Ry. Is this concept clear now? Now, with all this, this is kind of introduction. Now let's go back to see why we needed all of this. I'm going to get these things down again and analyze them. Let's say this is my system, right? you have Rx here, maybe Rx the other way. If I want to consider the free body diagram for one of them, right? For both of them, let's say this. I'm going to consider this as my system, right? That's what we did with the impact of two objects. If this is my system, do we have external forces here? Remember, FAB and FBA are action-reaction. They're internal forces. They cancel out each other. Do we have any external forces that you cannot cancel out? Yes or no? Technically, this Ry and Rx are not canceled out by anything. So you cannot use, because of that, since Rx and Ry are external forces, of course, unknown, we cannot use conservation of linear or angular linear momentum. In other words, if I write summation of L plus integration of, or let's just get MVG, that might be more. MIVGI plus integration of summation of forces dt, right, from T1 to T2 equals integration of MIVGI. This is 2, this is 1. If I write this equation, this term is not 0. Okay? So we cannot use this. What else we have to do? Look at here. Can I use conservation of angular momentum? If the whole thing is my system, if this is my system, can I use conservation of angle? Remember, angular momentum should be written about a point. So technically, the equation is summation of H about a point P1, right? Or let's just make it maybe O or G or whatever. I'm gonna keep the point empty for now, open, plus integration of M about that point dt equals summation of H about that point 2, right? The question is, what is this point? What should I put here? Can I put G? But if you put G, G goes for one of them. If I put this G or that G, it may not be useful. If I use the point O here, let's see what happens. Summation of H about O. Now let's just O, O, and O. If I do this, I can find the angular momentum of this object if it has a velocity like this. If we get the distance d, you can find H about O for object 1, or like H about O for A plus H How much is the moment applied around point O? Do these two forces create any moment about O? Kelly, the two forces, do they create any moment about O?
Yeah.
How much is it?
Would it be RX?
No, I'm
Oh.
talking about these two forces. FAB,
Uh,
FBA.
Yeah, they would, well, they cancel out.
They cancel out each other, right? So
Yeah.
now let's ask this question. Do these two forces, Rx and Ry, create any moment about O?
Yes.
How much is it?
Well, it'd be RX. And
Time
then,
times the
oh,
distance from O. How much is the distance of Rx from O?
would it be 0? So it
Zero,
wouldn't-
because reaction forces technically pass through the pin, right? Then these forces do not create any moment. These forces do not create any moment. Guess what? If I use this equation about O, then this will be 0, right? Which means now you can say the initial momentum, angular momentum before or after is the same. So for the oblique impact, what you can do is this. Consider the angular momentum, find the pinpoint, and make it 0. So like summation of H about O1 is equal to summation of H about O2 before after. All the explanation I gave was because we're going to get rid of these two because they're impulsive forces. Mg, we don't care because there are small forces. But this guy and this guy, the two forces are large and impulsive. One way to eliminate them is to use point O as the reference point for angular momentum and moment, right? So in short or in brief or in summary, if you have this guy pinned at O and you have this guy coming with some velocity anywhere, like it could be coming like this way, this could come rotate like this way, omega-1, because this is pin is either goes to the left or right. This is A, this is B, this is omega B1, this is VA1, right? If this happens, you're going to get large impulsive forces here and reaction forces here. Now, what you can do is this. Use conservation of angular momentum about point O, summation of H about O at 1 equals summation of H about O at 2. This is for eccentric impact. Now, remember, the velocities or angular momentums before impact is known. Right? We usually look for velocity omegas after impact, which means we will have two unknowns. right? This gives me one equation. This is equation number one. We need another equation to solve this. Where I'm going to get the other equation? Chris, where I'm going to get the second equation?
I'm not sure.
Okay. How about Jake? Jake B. Where I'm going to get the second equation?
I'm also not sure.
Heisey. I'm going to go one-on-one to see who's going to give me the answer. I need one more equation, right? Because, for example, this is going to have a velocity after impact. And if this is omega-1, omega-2 could be the same way or other way after impact. So I have two unknowns. How I'm going to get the second equation? I'm going to give you a hint. Do you guys remember how we get another equation for impacts in particles? We defined a physical parameter that defines the nature of impact.
The coefficient,
The coefficient of, you don't remember the name?
restitution.
Restitution. So again, remember, impact is not just hitting and bouncing back. It depends on the two materials hitting each other. For example, if this is, I don't know, a rigid plate hanging here, you can hit it with a basketball, right? Or you can hit it with a pizza dough. Or whatever is soft, right? Now, if you hit it with pizza dough, what happens? Let's say these two have the same mass, right? It's not going to have the same output. Or in another, let's say, give another example. You have a wooden plate hanging here. You hit it with a tennis ball, or you hit it with a bullet. Again, like tennis ball. And let's say they have similar masses. Your bullet is very large, right? Is the outcome the same? No, because tennis ball may bounce back, bullet may even penetrate inside and become one piece. So similar to particles, the impact output depends on the materials of the two rigid bodies. And then with this, you create or define coefficient of restitution, which is going to be the same definition. The relative velocity after impact and this is velocities at impact point. Which means if let's say this is point A and this is point B on the two rigid bodies, these are the two velocities of those points. And it has to be the perpendicular velocity, right? Not just any velocity. This gives you the second equation with this guy and this guy. You can find the final velocities of the two rigid bodies. Does that make sense? So because of large impulsive forces, I could not use conservation of linear momentum because we don't know these forces. It's just going to create extra unknowns. So I was limited to angular momentum around this point, so I can eliminate the reaction forces. And then the second equation, as always, comes from the nature of the materials and how they bounce back or stick together or whatever happens, and that's coefficient of restitution. Very boring stuff, right? We're going to do a couple of examples and you see how this works. Let's go back to the slides and see what we got here. So the slides are kind of nicely and briefly explain what I just said. We're going to use the principle of angular momentum about O, and also you can use the coefficient of restitution. Remember, this is not velocity of any point. Has to be the velocity of the contact point. For particles, we don't have to emphasize on the velocity of contact point because we assume the entire particle has the same velocity, right? But for rigid, imagine like this is like my hand, right? If it rotates, this point and this point and this point, they don't have the same velocity. So if something hits here, you're going to have one velocity. If something hits here, you have another velocity. You have to find the velocity of the contact point. Any question? Does that make sense? Okay. And remember, the velocities are in the direction of impact line. If it goes this way, you have to get the perpendicular velocity. Let's do this example. This is like kind of simple example. Most of examples you have are like this, right? So here you have a 4-pound rod. This is a slender rod hanging from point A. You have a 2-pound block with the initial velocity of 12 feet per second. So it's sliding here with a constant velocity. When it hits B, you're going to have this eccentric impact, right? After this hits B, you may expect B to kind of start rotate to the right. The block may go to the right or left, depends on the equations, obviously. The coefficient of restitution is 0.8. The problem says find the velocity of the block, of course, and the velocity of the rod after the impact. I'm going to give you a minute to get this done, get the numbers and everything. So the parameters are, or the units are in imperial units. So you have to get the velocity So get the masses in slug. Let's switch to the tablet. So the rod has a mass of 4 pounds. The block has a mass of, the weight of 2 pounds. Then L here is 3 feet. And V1 is 12 feet per second. And coefficient of restitution 0.8. I know the explanation with those weird shape kind of may have confused you. Now you can see here easily how we apply that. As we explained, this is a case of eccentric impact. If that's the case, the hinge point is point A. So I'm going to write conservation of angular momentum about A. Now, when we talk about angular momentum, we know that particles like this could also have angular momentum, right? Let's call this particle as, I'm going to just call it as C so we can use it. So the angular momentum of C about A, H about A for C is going to be MC VC times the distance. The distance is this much, right? If you neglect the size of this and suppose that it just goes to the tip. Any question about this? This is how you find the angular momentum of a particle. Velocity times distance, right? I think the problem says that the rod is stationary at the beginning. Yeah, it doesn't say anything about its motion, so we suppose the rod is stationary. If that's the case, so technically H about A is H about A for C plus H about A for rod, right? Now, before impact, and we can write this as MC VCL. How much is the angular momentum of the rod, this rod? How much is the angular momentum of this rod about A? Do you remember? Anyone? The angular momentum of the rod about A. It should be IO omega, right? Or IA omega. And I of a rod about A, you know what, let me just move this down. So I about A is ML squared by 3. So then this guy, rod, is going to be M rod L squared by 3 omega. So if you substitute it here, you're going to get M rod L squared omega 1/3. This is overall H about A. Before impact, omega is 0. So H about A before impact, which is position 1, is going to be simply MC V1L. After impact, H about A is going to be MC V2. It's going to have another velocity, I don't know how much, times L plus 1/3 MR L squared omega 2. So these are velocity components, linear and angular, after impact. Right? Now, if I use the conservation of angular momentum, I should say H about A at 1 equals H about A at 2. If I substitute, I'm going to get MC V1L is equal to MC V2L plus 1/3 MR L squared omega 2. Let me put this V outside that so we can just show. Right? This is one equation with 2 unknowns. Again, where I get the second equation? Callie? The second equation?
The coefficient of restitution.
Exactly. So I'm going to get E is equal to, now remember, this is, look at here for a second, please, everybody. This is the contact point, right? This big dot. So the velocity of the block before and after, because it's just a slice, is the same. The velocity of the rod at this point, how much is the velocity? It should be velocity of B, right? And how much is it? Like VB is equal to? Anyone?
Omega AB times RAB.
Exactly. Omega AB, which we call it omega 1 or 2, and RAB, let's just omega AB, RAB, which is omega times L, right? Before and after, this is the velocity. So if I use this in coefficient of restitution, I'm going to get omega 2 L, this is VB2, minus VC2 divided by VC1 minus omega 1L, right? You remember you flip the 2 terms in the numerator and denominator. As I said, omega 1 is 0. So this is going to give you simply E V1 is equal to L omega 2 minus V2. equation 1, equation 2, you calculate it, you can find the two unknowns. For example, from 2, you may say V2 is L omega 2 minus E V1. Substitute it here. I'm going to give you 2 minutes. Please, everybody, try this because I want you guys to get used to these equations and work with it. I know it's just simple plugging in the numbers. And remember, these are weights, so you have to get M of rod. It's going to be 4 divided by 32.2. M of block, which we call it C technically, because we call this C, it's going to be 2 divided by 32.2. You're going to put these two numbers, these two equations, and solve it. 2 minutes to finish. These are the two numbers you need to have. Let me know if you've got the same numbers.
I got the same numbers.
You got?
Yeah.
Okay. Anyone else? So that is how. Okay, great. So that is how you use conservation of angular momentum for eccentric impact. Okay. Any question? Now let's do one more example. I'm going to go back to the slides. We're going to do this example. In this example, you have a pendulum, has a sphere at the end, 10 pounds, and a rod, 4 pounds. It is released when theta is 90 degrees. Technically, it is released when it's vertical. When you release it, it's going to come down, hit the ground, and bounces back. It says, find the rebound angle after it hits the ground. So technically, this problem or problems like this have three parts. The first part is going from top position to the horizontal position when it hits the ground. The second part is to consider the impact, and the third part is to consider rebounding after the impact. So let me switch to the tablet and tell you what happens. Look at here for a second, please. This is position 1 when theta is 90 degrees vertical. You release it, it's going to go down and hit the ground at position 2. Interestingly, position 3 is right after the, remember, when impact happens, things don't move as much, right? It hits, I don't know if you can see my hand, it hits the ground and is about to bounce back. So technically, position 3 is the same location, right? 2 is before impact, 3 is after impact. So after impact, it has some velocity to go up. And if it goes up, it will go up to a certain degree, like that's actually what we're looking for. So it's technically moving from that position, horizontal, to like this position, right? This is final theta. And this is going to be position 4. So we have three processes or three things happening that we need to process. Okay, let me just write the values here. As I said, it's always easier. So if this is L, L is 2 feet. The radius of this guy, R, is 0.3 feet. Then W of a sphere is 10 pounds, and W of rod is 4 pounds. And we have point O here. The problem gives you this distance as 0.3, which means because this is 0.3, when it hits the ground, it's going to be horizontal the way I draw it. Okay, you have to find M of a sphere, which is 10 divided by 32.2, and M of rod, which is 4 divided by 32.2. We're going to calculate this later. Now, I also need the moment of inertia of the whole system about O, right? The whole system, if I use something to kind of, let's just go with blue. This is the whole system, right? This blue system, which is made of a rod and a sphere, is going to be I rod plus I sphere. I rod is M L squared by 3. I sphere is 2/5 M R squared plus the distance M D squared, which is going to be 2/5 M R squared plus M times L plus R squared, right? You can calculate this and find out the I. Now, let me calculate these masses. 10 divided by 32.2 0.3106 and 4 divided by 32.2 0.1242. The unit is slug. If you put all the masses, this is for sphere, obviously. This is for rod. If you put all the values, I'm not going to go through the numbers, you can check it later. You're going to get 1.8197 slug with the square. So this is your I about, oh, sorry, not this one, the whole thing. I about O will be 1.8197 slug with the square. We need this for multiple purposes. Okay, did you guys write this? So let me move the whole schematic down so we can deal with it. As I said, we have 3 steps here. And let's get rid of these things. We know what this means. From 1 to 2, what happens? When this goes and hits the ground, what happens? When it's, I don't know if you can see my hand, when it's vertical, it has all potential energy. When it goes down and hits ground, that potential energy turns to kinetic energy, right? We don't have any non-conservative force, which means this is 1 to 2 is conservation of energy, which means T1 plus V1 equals T2 plus V2. Now T1 is 0 because it doesn't move at the beginning, is at rest. T2, the whole object here is a rigid body rotating about fixed point, right? So if that's the case, then T2 is going to be half IO omega 2 squared. There's no spring here, so when we want to calculate V1, is always on just gravitational potential energy. Look at here for a second, please. Just stop for a minute writing. Now we have 2 objects. The center of gravity for a sphere is here. The center of gravity for this is like G sphere, and this is G rod. And I need a reference point to measure those or calculate those gravitational potential energies. So I'm going to use this as my reference for Y, right? If that's the case, then for V1, we're going to get M of the sphere, G, look at the height here, is R plus L, right? So we're going to get R plus L. And for the rod, this is the height, which is L by 2. So this is T1, sorry, V1. Now, considering the entire system goes through this line, V2 is simply 0. Which means this equation, equation 1, will turn to simply MSG R plus L plus MRG L by 2, all potential initial potential energy is equal to half IO omega 2 squared. And the only unknown here is omega 2. I'm going to give you a minute to calculate this. You have all the numbers, the masses, the moment of inertia, and the dimensions. And you should get this number if you solve them. Did you guys get the same number?
Yeah.
Okay, good. So this is what happens between 1 and 2. Okay. Now, between 2 and 3, remember, look at here for a second, please. Technically, 2 and 3 are same position. 2 is when this goes down. 3 is when it bounces up. Exact same point. Just before hitting the ground and just after hitting the ground. So practically, the pendulum doesn't move as much, right? Just before hitting and just after hitting. So its position is the same. It's just the velocity once goes down, once goes up. So between 2 and 3, because it is an eccentric impact, we're going to use eccentric impact. Now, something interesting. You remember for the particles, I said when you have one of the object as ground, you cannot really use the conservation of momentum because you don't have the mass of the ground, right? The velocity, but the good thing is ground doesn't move, so the velocity before and after is 0. So I'm going to write again here, when ground is one of the objects, its velocity before and after impact is 0, which means you don't have to calculate its velocity. You lose one unknown. We lose one unknown. And of course, we lose one equation. And that equation is the conservation of momentum For particles, it was linear. Now here, angular momentum. Which means I cannot use HO1 equals HO2. You cannot use this. Luckily, we don't need it because the velocity of ground remains 0, right? So we have one equation. And so if that's the case, we can use E to find the unknown. In this case, now, pay attention for here for a second. One object is ground, right? Remember, again, the point of impact is here, right? So I have to find the velocity of pendulum at this point, right? So if you write VB2 minus V ground 2, V ground 1 minus VB1, V ground before after is 0. And VB, technically we should, because I wrote 2 and 3, let me just write it 2 and 3 so we are consistent with those numbers, okay? Three means after impact, 2 means before impact, based on what we have here. And VB3 is going to be the radius. Look at here again. The radius of rotation is L plus R, right? So you're going to get L plus R omega 3. And the velocity of bouncing is up, is positive. You can say, look at here for a second, please, everybody. It doesn't matter if down is positive or up is positive, but you have to stick with that convention one way or another, right? I'm going to assume that up is positive, as I highlighted here. So V3 that goes up is positive, V2 that goes down is negative. So VB3 is going to be this, and VB2 is going to be minus L plus R omega 2. If I substitute here, you're going to get L plus R omega 3 minus L plus R omega 2. So technically you cancel out this. E is omega 3 by omega 2, which means omega 3 is E omega 2, which is going to be, how much is 0.8? So your omega 3 is going to be 4.358 radian per second. This is what happened right after the impact. Any questions so far? So we had 3 stages for position: 1 to 2, 2 to 3 before after, and 3 to 4 when it bounces back and somewhere stops in the air until it bounces back again, right? 1 to 2 was conservation of energy, as you can see here. 2 to 3 was eccentric impact. Now, if I want to go 3 to 4, what is 3 to 4? Look at here. Look at the schematic. This is position 3, and this is position 4. It hits the ground and bounces back up to here. Similar to 1 to 2, it went down with energy. It goes back with energy equation, right? You guys follow? Any question? You guys seem to be puzzled. Huh, Callie? Is it too much?
No.
It's good. Heise is good. Yoon? Okay, so from 3 to 4, I'm gonna just do it. From 3 to this is 3, right? And this is 4. Again, conservation of energy. This is like G of rod. This is G of a sphere. If this angle is theta, we need to find these Y values. Right? Now you're going to get T1 plus, or like, let's just go 3 and 4. T3 plus V3 equals T4 plus V4. T3 is half IO omega 3 squared. T4 is 0 because at this position, this is the maximum, it's going to momentarily stop. Then V3, again, if this is your Y, it's going to be 0. And V4, look at here for a second, please. This is G for rod. This is G for a sphere. The height above the reference point is this much and this much. I'm going to have to calculate that. And if I do that, then this is going to be M rod G. This height is L/2 sine theta. And M sphere G, this height is going to be L plus R sine theta. So if I put all of this in the same equation, you're going to get half IO omega 3 squared. It's M rod G. Let's just put it like that. M rod G L/2 sine theta plus M sphere G L plus R sine theta. In this equation, your unknown, is sine theta. Make sense? Now, if you solve this for theta, everything else you know, omega 3 you calculated, everything else you know, if you do that, your theta is going to be 39.8 degree. And I think the sine theta should be something like this, because I don't have sine inverse. I have to go that way. 39.8 sine theta should be like 0.64 or something like that. Right? Any question? I know this seems to be too much, but this was a good example of showing you like kind of a review conservation of energy. The main part for us was eccentric impact. We had examples, previous one, you know, the block hitting the the rod, you use it regularly. Here, the ground is involved. You cannot use this. You're going to limit it to that. So that was another example to show you how you can use it. And after this, again, conservation of energy. So I think this example captures different aspects of potential problems you can solve. Okay. I know we are like 2-3 minutes over the limit. Just give me 2 more minutes. I'm going to clarify or like review a few stuff. The homework for chapter 17, I think, is due tomorrow, right? Okay. This Friday, we're going to have the final exam. And I know it's kind of squeezed. I'm going to post the homeworks for this chapter later today. It's going to be due. Let's just make it due Wednesday midnight. Okay? Because I want to post the solutions on Thursday and give you another day to review them so you're getting ready for the final exam. So you have one set of homework due tomorrow, which I gave you like 10 days ago. And you're going to have some homework for this chapter. I'm not going to make it 6, maybe 2 or 3 only, just to practice, okay? And it's going to be due on Wednesday. On Wednesday, I will solve maybe 3 problems covering particles and rigid bodies and everything, right? I try to find problems that cover different parts of it. Like this one also has energy concept in it, right? And like calculating moment of inertia, all of that. I try to find 3 problems. Because you have homeworks, I'm not expecting you guys to spend time with those problems. So I was going to post it for you guys to have a look at it, but you have 2 sets of homework. Probably you don't get time to do that. On Wednesday, we're going to review 3 problems. Hopefully we can finish 3. And on Friday, we're going to have our exam. Like all final exams is going to be 100 minutes. I know we have more than 100, but if I make it longer, it's going to be more problems. You guys will be probably tired, right? 100 minutes, probably 4, most likely 4, maybe 5, if there's simple or shorter 5 problems. And that's it. Meanwhile, if you have any question, if you need help with any part of the course, I barely had anyone coming for office hours the whole past 8 weeks. You still have 3 more days to do that if you need. I'm available mostly because, you know, I may have been busy with my personal stuff, but I've tried to make time same day to meet with you, even if it's later in the afternoon, okay? Any question? Did you guys enjoy the lecture? So we are officially done with all the chapters. As I said, Wednesday, some reviews, and you have some homework to do, and I see you on Wednesday. Enjoy the rest of your day and have a good day. Bye.